Welcome to the Joy of Math. I'm Arthur Benjamin, Professor of Mathematics at Harvey Mudd College. Now, many people, when they hear the joy of math, boy, that sounds like a contradiction in terms. I mean, for many people, math is a four-letter word, something to be afraid of, not something to be in love with. And yet, in these lectures, I hope to show you why mathematics is indeed something to love. There are many, many reasons to love mathematics. In fact, I call these the ABCs of loving mathematics. You can love mathematics for its applications, for its beauty and structure, and for its certainty. And I'll say more about these. For instance, what are some of the applications of mathematics? Mathematics is, after all, the language of science. The laws of nature are written in the language of mathematics, particularly in calculus and differential equations. We'll learn about calculus in these lectures. Calculus is how things change and grow over time, modeling everything from the motion of pendulums to galaxies. On more down-to-earth subjects, mathematics can be used to model how your money grows. We'll talk about the mathematics of compound interest and how it connects to the mysterious number E. More prosaically, mathematics can be used in daily life decisions, such as which phone plan should we be getting? Or mathematics can literally bring order to your life. Like, take for instance those 8 books on the bookshelf behind me. If I asked, how many ways could I arrange those 8 books? How long would it take? If let's say we arranged those books in a different order every day, how many days would we have to do this until we saw all possible orderings? Would you believe with just 8 books, it would take 40,320 days, literally over 100 years, before you saw all 8 arrangements. And if there were 12 books behind me, well, forget it. There would be almost 500 million ways of arranging 12 books. When I was a kid, I loved mathematics primarily for its consistency. I loved the fact that you could take a math problem, do it lots and lots of different ways, and if you were careful, you'd always get the same answer. I love doing math problems, especially doing math problems in my head. And I figured out lots of different strategies for doing math in my head really quickly, and I'll share many of those with you. I think, by the way, that mathematics is often taught as an exercise in disciplined thinking. And some people like that, right? That is, if you follow your instructions carefully and don't make any mistakes, you'll always wind up with the same answer. And so mathematics can train people to following directions carefully. However, I think that there's plenty of things in our curriculum that will teach people disciplined thinking. Mathematics can and should also be used as an opportunity for creative thinking. Not simply, solve this problem one way, but solve the problem several different ways. There's more than one way to solve a problem. Frankly, I think that's a valuable life lesson that we all can learn, right? There's not just one way to go after a problem, but look at multiple approaches. Let me give you an example of the sorts of things that I thought about when I was a kid. I can remember sitting on a bus one day, and I was thinking, like many children would, of the numbers that added up to 20. All right, I know, I was a strange kid. Okay, but bear with me here. I was thinking about, among those numbers that added up to 20, how large could the product get? And I thought it would happen in the middle, right, with 10 and 10. When you multiply those numbers together, you get 100. And I wondered, can you get higher than 100, or is that the best you can do? So I tried various numbers. I did 9 times 11, 8 times 12, 7 times 13, 6 times 14, and so on. And I looked at the answers. I saw that we got 99, which was almost 100, but it was shy by 1. And 8 times 12 was 96, which again was almost 100, but it was shy by 4. And 7 times 13 was 91, and 6 times 14 is 84, 5 times 15 is 75. And I noticed two things. I noticed, first of all, hey, those numbers, those products, are getting smaller. As I bring those numbers farther and farther apart from 10 times 10, that those products were getting smaller. But what was really intriguing was how far those products were away from 100. They were 1 away, 4 away, 9 away, 16 away, 25 away, and so on. And I said, hey, hang on, I recognize those numbers. Those numbers are perfect squares. That's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. I wonder if that always works. So I thought about the numbers that added up to 26. Started in the middle with 13 times 13, and I tried the same thing. Let's see, 13 times 13, that's 169. I worked that out the long way. Then I tried 12 times 14, which was 168, which was shy by 1. 11 times 15 was 165, which was shy by 4. 10 times 16 was 160, which was shy by 9. And the pattern continued. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And then I had a creative thought. I said, hey, not only is this pattern beautiful, but this pattern could also be put to use. Let's say you didn't know what 13 times 13 was. Well, instead, let's do an easier multiplication. Let's do 10 times 16. That's an easier product to do, right? 10 times 16 was 160. And now you just have to adjust your answer by adding up that you are 9 away. Since 10 and 16 were each 3 away from 13, all you have to add is 3 squared. 160 plus 9 is 169, and that's an easier way to calculate 13 times 13. In this course, I'll go into more details about how to square numbers and multiply numbers in your head faster than you ever thought possible. Let me give you one more cute example here, which I think is pretty intriguing. Let's multiply two numbers that are close to 100, okay? Look at the numbers 104 and 109, okay? And I'll write next to them how far each of those numbers are away from 100. So 104 is 4 away, and 109 is 9 away from 100. All right, now, next step, all we do is we take 104 plus 9 or 109 plus 4. Take your pick, you'll always get the same answer. What do you get? Let's see, 104 plus 9 is 113. Good. Next, multiply those two one-digit numbers together. 4 times 9 is 36. Write that down. And believe it or not, you've now written down the answer. The answer to that multiplication problem is 11336, 11,336. And we'll see why that works in The Joy of Math. When I was a teenager, I loved to play games. Boy, I was addicted to backgammon, chess, poker, and I still am as an adult, I confess. And I saw that many of these games used math in some way. And so what I found was that by understanding math, especially areas of math like probability, or my favorite area of math, combinatorics, which is a fancy way of saying clever ways of counting things, I found that I could be a better game player and actually win more. And so I'm going to share some of those secrets with you in this course as well. We'll use math to analyze games like poker, roulette, and craps. And we'll learn about the long-term effects of playing some of these games. But throughout these lectures, I want us to have lots of fun, okay? These lectures are going to include a song, a dance, poetry, games, a few magic tricks, and lots of bad jokes, I'm afraid. We'll learn about the number pi, including lots of trivia about pi. I'll teach you how to memorize pi to 100 places, beginning with a sentence about, of all things, my turtle. On the last day of class, we'll have a party, no exam, I promise, with some magical entertainment. You'll also be exposed in this class to math ideas from high school level mathematics to college level mathematics, all the way to unsolved problems in mathematics. You'll learn what is 5 factorial and why should we care. We'll learn about many of the fundamental theorems in mathematics. You'll learn the fundamental theorem of arithmetic, the fundamental theorem of algebra, and even the fundamental theorem of calculus. And along the way, we'll encounter some of the great historical figures in mathematics, people like Euclid, Gauss, and Euler. You'll learn why 0.9999999 going out forever is actually equal to the number 1. Not just close to it, but equal. You'll understand why sine squared plus cosine squared is 1. You won't have to just take my word for it. You'll actually have an understanding of that. And you'll re-encounter the Pythagorean theorem, and we'll have a proof of that. You'll actually be able to follow the proof and not only know what the Pythagorean theorem says, but why it's true as well. Again, the B in loving mathematics is because mathematics is beautiful. We'll study some of the beautiful numbers in mathematics, E, pi, and I. E, I will convince you, is the most important number in calculus. Pi, of course, is the most important number in geometry and trigonometry. And I is the imaginary number. I is the number whose square is equal to -1. Now, can you imagine that? A number whose square is -1? What good could possibly come out of a number like that? And yet, we'll come up with some very beautiful and useful mathematical formulas. In fact, the next formula, e to the pi I plus 1 equals 0. Some people consider that to be one of the most beautiful formulas in mathematics. There in one equation are you using e, pi, I, 1, and 0, arguably the 5 most important numbers in mathematics, along with addition, multiplication, exponentiation, and equality. Another beautiful aspect of mathematics is patterns. Mathematics is the science of patterns. And one great place where patterns live and celebrate is Pascal's triangle. We'll have an entire lecture devoted to Pascal's triangle. Let's take a look at it here. Look at the triangle. It has ones along the borders and other numbers in the middle. The numbers in the middle are created by taking 2 adjacent numbers, adding them together, and writing their total underneath those 2 numbers. Like that 4 plus the 6 creates the number 10. Okay, looking at this triangle, there are many patterns we can find. Here are just a few of them. If you add the numbers across each row, take a look at what you get. The first row adds up to 1. The second row adds up to 2. The next row adds up to 4. The next row adds up to 8. Then 16, 32, 64. Do you see the numbers we're getting? We're getting the powers of 2. Here's a more subtle pattern. Imagine adding the diagonal sums of this triangle. Okay, so the first diagonal adds up to 1. The next diagonal adds up to 1. The next diagonal adds up to 2. The next diagonal adds up to 3. Let's look at these numbers. The next diagonal, 1 plus 3 plus 1, is 5. Followed by 1 plus 4 plus 3, that diagonal adds to 8. And then we have 1, 5, 6, 1, that adds up to 13. And look at the sums that we've been getting. 1, 1, 2, 3, 5, 8, 13. These are the mysterious Fibonacci numbers. And these numbers show up everywhere in mathematics. They're some of my all-time favorite numbers. Mathematics is intriguing. And perhaps nothing is more intriguing than the notion of infinity. And we're going to study infinity both as a number-like object as well as the size of an object. We're going to show that there are some sets that have an infinite number of objects, other sets that have an infinite number of objects, and yet some of those sets are going to be substantially more infinite than others. We're going to see that there are actually different levels of infinity that have very many beautiful as well as practical applications. Speaking of infinity, we'll have some fun adding up infinitely many numbers. We'll see that if you take a series like 1 plus a half plus a fourth plus an eighth plus a 16th and so on, adding up with all those denominators being powers of 2, I'm going to show you 2 ways of showing that the sum of those numbers is 2. We'll see it both from a visual perspective as well as from an algebraic perspective. And yet, paradoxically, here's another set of numbers, a simpler set of numbers, where the terms are also getting smaller and smaller. 1 plus a half plus a third plus a fourth plus a fifth plus a sixth. Even though those terms are getting smaller and smaller and getting closer and closer to 0, in this case, the sum of those numbers, this is called the harmonic series, is actually infinite. And what that means is that sum will eventually get higher than 10. It'll eventually get higher than 100. It'll eventually get higher than 1,000,000. That's what it means for that sum to blow up to infinity. Speaking of infinite sums, we'll encounter many paradoxes once we enter the land of infinity. We'll find a collection of numbers, an infinite collection of numbers, so that when you rearrange those numbers, you get a different sum. That can't happen in a finite land, right? 3 plus 4, it will always be 4 plus 3. And yet, when you add an infinite number of numbers, the commutative law of addition can actually fail. Speaking of paradoxes, here's another question I have for you. Imagine you had a party and you invited a whole bunch of your friends at random. What is and you want to figure out the probability that 2 people at the party actually share the same birthday. Forget about the year, just the same month and day. How many people would you need to invite in order to have a 50% chance that 2 people would have the same birthday? Do you think you'd need 50 people? Maybe 100 people? Would you believe the answer is just 23 people? With just 23 people, you have a slightly better than 50% chance that 2 people in that room will actually have the same birthday. And we'll prove that for you. I'll also prove for you, in a tongue-in-cheek sort of way, that all numbers are interesting. So if you doubt my word, we'll actually be able to prove that all numbers are interesting. But seriously, another reason why people love mathematics is because it actually allows for absolute certainty. This was the C of loving mathematics. In no other discipline can you show things to be absolutely unmistakably true. It's the only subject that allows it. For instance, if you could show, as the ancient Greeks did, that there are infinitely many primes, okay, that the number of prime numbers goes on forever, that theorem will also go on forever. It's there, it's established, and nothing that we can do is going to change that. The Pythagorean theorem is just as true today as it was thousands of years ago. And in this course, you'll learn many powerful techniques for proving theorems. Frankly, I've often thought that the best road to immortality was to be a mathematician and to prove a theorem, to be the first person to discover a new mathematical fact, because that has a chance of living for thousands of years. It's not like these are theories that will go out of date every decade or century or two. Theorems, like ideas, can last forever. Not only can you prove things with absolute certainty, mathematics also allows you to prove that certain things are impossible. Now, you've probably heard people say, oh, you can't prove a negative. Oh, yeah? Well, in mathematics, you can. You can prove, for example, that the number square root of 2 is irrational. What does that mean? That means that no matter how hard you try, you cannot write the number square root of 2 as a fraction, where you have a whole number, an integer in your numerator, and an integer in your denominator. It's not like we can't do it because we're not clever enough. It's not like we can't do it because we've tried a million examples and we haven't been able to find one. We can absolutely ironclad prove that it is impossible to write square root of 2 as a fraction. In the same sort of way, we can prove, although we won't do it in this course, that the number pi is irrational and never repeats. That is to say, you're never going to find a regular pattern repeating in a regular sort of way in the beautiful number pi. Now, how should we use this course? I mean, the lectures in this course were designed to go in a certain order, okay? They're in an order that feels very natural to me. But it is okay to skip around, okay? I don't want you to get hung up on one lecture. Let's say you start getting confused in the middle of one of them. That's okay. Don't give up. Keep on going. I think these lectures are worth repeating. I have a lot of material I want to show you. There's just so much I want to tell you. Sometimes I get a little overexcited and I may go a little bit fast, but that's okay. You have the power of the remote control. You can rewind me and have me explain it all over again. In fact, some of these lectures are actually going to make more sense to you after you've gone beyond them. Okay, some of the lectures, for instance, use a little bit of algebra before we actually start talking about the joy of algebra. So it's okay to come back and revisit this material. I think all the material bears repeating, and I hope you get to enjoy it many times over. Let me quickly talk about the specific topics that we're going to cover in this course. We're going to learn about the joy of numbers, the joy of primes, the joy of counting, and maybe the joy of my favorite numbers, the Fibonacci numbers. We'll have a few lectures talking about the joy of algebra, because that's one of the most useful mathematics courses beyond arithmetic. We'll talk a little bit about the joy of 9, and what does that mean? You'll have to see that lecture for yourself. The joy of proofs, that is, how do you actually absolutely ironclad prove things to be true? We'll talk about the joy of geometry and the most important number in geometry, the number pi. We'll learn about trigonometry, sines, cosines, tangents, triangles, and circles. We'll learn about the joy of the imaginary number I, a number whose square is -1. And after I, we'll learn about the other vowel in mathematics, the number E, and why that shows up all over the place. We'll talk about the joy of infinity, the joy of infinite series, what happens when you add up an infinite number of numbers. And all that sets the stage for 3 lectures on the joy of calculus, how things grow, how we integrate things together. After that, we'll have some fun. We'll have fun in all of these lectures, I hope, but we'll take a little bit of a break and study the beauty, the glory of Pascal's triangle, and apply some of those ideas to the joy of probability and the joy of games. And then we'll end everything with one great mathematical magic show when we talk about the joy of magic. Which, by the way, one more special reason to love math, it doesn't fit the ABC pattern, but I think mathematics is magical. Truly, in addition to being a professor of mathematics, I'm also a professional magician. I've performed magic most of my life, and I find that math and magic have an awful lot in common. For instance, in both cases, when you're looking at math and magic, you're solving a problem or a puzzle based on limited information. And part of the fun about doing a math problem or figuring out a magic trick is trying to understand how it's done. What's really going on here? And when I teach my courses at Harvey Mudd College and my courses for you, I always try to present the material almost as a magician would, with elements of humor, surprise, and elegance. If I can't convince you that mathematics is magical yet, here are a few more reasons to consider. I will teach you in this course how to square numbers in your head, maybe if you practice faster than a calculator. I'll teach you how to figure out the day of the week of any date in history, so that somebody could say be born in November 18th, 1936, and you'll be able to say with certainty that was a Wednesday. I'll teach you about the joy of magic squares, and I'll even teach you how to do cube roots in your head. So that, for instance, if somebody said, I just cubed a two-digit number, and the answer was 658,503, you can say with certainty and confidence that the cube root was 87. So I hope after this course that you'll benefit in many ways, that it will change the way you think about numbers and about life, that you look at problems from many different perspectives. I mean, for example, to use a mathematics analogy, we'll look at the trigonometric function, the sine function, and we'll see that in three different ways. We'll see that, for instance, in terms of a right triangle, that the sine of an angle A is equal to the length of the opposite side divided by the length of the hypotenuse. We'll think of the sine function in terms of the unit circle. That is, given an angle A, we can look at the point xy on the unit circle corresponding to that angle, and the sine will be the y coordinate of that point. And we'll even look at the sine function from an algebraic standpoint. That is, we'll be able to calculate the sine of A. For any angle A written in radians, we can write that as A minus a cubed over 3 factorial plus a to the 5th over 5 factorial minus a to the 7 over 7 factorial, and so on. We can write the sine function as an infinite sum. Now, I know what some of you are thinking right now. You're thinking about something that I saw in the movie Peggy Sue Got Married. It was a great movie. Peggy Sue goes back in time like 20, 25 years, and she finds herself back in high school. You know, there she is. How she got there, she doesn't know. And she's following her friends. She walks into class and discovers that there she is in her old high school math class. It was something like Algebra 2. And they're giving a test, and all the students are stressing out over it. And she's looking at the problems here and there. And she casually walks up and goes to the teacher in front of the room and says, I can say with certainty, I'm never going to need this stuff. And yet, I hope that, in fact, there are many reasons that you'll benefit by going through the joy of mathematics. Mathematics, after all, is food for the brain. It'll teach you how to think precisely, decisively, and creatively, even if you never use a trigonometric function in your life. Math helps you to look at the world in a different way. Whether it be quantifying decisions in your daily life, like which mortgage offer should you take, to being able to appreciate a fine proof, a beautiful mathematical argument, in much the same way that other people can appreciate great poetry, painting, music, and fine wine. That is, I hope by going through this course, you'll find joy in mathematics. It's another way that you can find joy in your life, and your life will be richer for it. So let me conclude by saying, if you don't know the difference between a logarithm and an algorithm, a radian from a radius, or a polygon from a polynomial, then please join me as together we explore the joy of math.